Okay, I'm going to start this video one more time. We're going to learn about angular momentum and its conservation. I've extended the homework until the 20th so that both of you can finish it. And we're going to cover the last part of this chapter, and then I'll try to make some video about any problems that you have questions about. That angular momentum, similar to linear momentum, is conserved. Linear momentum being P equals m times v, mass times velocity, and angular momentum, we replace again the mass with the inertia, the moment of inertia I, for a particular shaped object and its mass, calculated previously in this chapter. And then the rotational velocity, or the angular velocity, omega. So I omega instead of m times v. And it's conserved, and they talk about how the Earth is spinning because of the original rotation of all the parts of the Earth that came together over the eons as it formed, and it's still spinning today. And that's conservation of momentum. Very simple concept, I think. But let's put it into practice. So here, let's calculate the angular momentum of the Earth. Since the Earth is a solid sphere, more or less, we're going to approximate the moment of inertia of the Earth as the moment of inertia of a sphere of mass m, where m is the mass of the Earth, and that ends up being 2/5 mr squared. So we go ahead and calculate that, and then the moment of the angular momentum is that I, or that moment I, times the rotational velocity of the Earth, so the angular velocity of the Earth, which happens to be one rotation, or 2 pi radians, every day, which is 24 hours times 60 minutes per hour times 60 seconds per minute, and then we can get that in seconds. So we have to do a conversion to that, for sure. And here they go ahead and they calculate that I, and that 1 revolution per day gets converted using 60 seconds and everything else, and then we end up with a total of 7.07 times 10 to the 3 kilogram meters per meter squared per second. Which is a big number. A lot of angular momentum. And of course, just like with linear momentum, there's a relationship between force and momentum for angular momentum, except it's not force, it's torque, since torque is the thing that we use to replace force when we're talking about rotational dynamics. We said that the net torque is equal to the change in momentum over the change in time, and so that there is a relationship between torque and momentum, and rather than force and momentum. Here's the similar one for force. Force equals change in momentum, linear momentum over change in time. And it's a very useful equation. So here we have a tray of food that we're going to rotate here, lazy Susan as they call it, and a person is going to exert up to 2.5 Newton force perpendicular to lazy Susan at the radius, and so we should be able to calculate that torque. And we want to know the final angular momentum. Well, it's going to need some time, and they do give some time. They say that if they're going to apply this torque or this force for 0.15 seconds, and we'll see what the final momentum is. Well, we are going to know the net torque because we're going to be able to calculate that from the force and the angle and the radius. And then we'll know the change in time, so we should be able to calculate delta L. We rearrange the equation so that delta L equals the net torque times delta T, and so the torque is equal to the R times the force, the radius times the force, and the radius times force times delta T. And those numbers are just numbers they've given us. We just plug them in, boom, 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 and we get 9.75 times 10 to the minus 2 kilogram meters squared per second. A whole lot of difference between that small torque that we've given to the table and the torque on the Earth, of course. Or not the torque, but the angular momentum of the Earth. So very, very small angular momentum for the table, that is a very, very small mass and it's not moving very fast. If we want to know the final angular velocity, we just set that angular momentum equal to I times omega and solve for omega, and then the I is the I for a disk or a disk of whatever of mass m, so it's 1/2 mr squared from the table that we look at, from the chart that we looked at in the previous page in the chapter. So in this next problem, next example, we have a person who's kicking a ball, and he's exerting a 2,000 Newton force with his upper leg muscle. Perpendicular lever arm is 2.2 centimeters, and we're looking at we have a moment of inertia of the lower leg of 1.25 kilogram meter squared, so we'll just calculate that for us. The acceleration, the angular acceleration of the leg, we want to know. We want to neglect the gravitational force. We want to know the rotational kinetic energy of the leg after it's rotated through a certain amount of angle, and so on and so forth. So we're going to have to do some math. First, part A, angular acceleration. Well, angular acceleration is going to be related to torque. So torque equals I times alpha, just like force equals mass times acceleration. So it's I times alpha. And the torque is related to also to the distance, the radius, and the force, and they've given us those things, so we can calculate the torque. 0.022 meters, or the 2.2 centimeters, times the 2,000 newtons, so 44 newton meters of torque on the leg going on there. And then that torque is also equal to I times alpha, and so we solve for alpha, and we end up with torque divided by I, and they've given us I, so we plug that in. Get 35.2 radians per second squared for the angular acceleration. And then the final angular velocity of the leg is going to end up being calculated using some kinematic equations for rotation. So final angular velocity equals initial angular velocity, and those are both squared, plus the 2 times the angular acceleration alpha times the angle that we've moved through, which is theta. And we have no initial angular velocity, so this just ends up being this equation. We take the square root of both sides, and we get the value that we are looking for, which we missed somehow. Well, anyway, I guess they don't finish this problem, but anyway, that's omega. Oh, they do finish it on the next part. So here's the omega squared is equal to 2 alpha times theta, and they actually want to know the kinetic energy. And we need omega squared for the kinetic energy, so we just plug it in like that. So Ke equals 1/2 I omega squared, so it's 1/2 I times on this page times 2 alpha omega. 2 times the angular acceleration times the angle. So that's what we end up throwing in there, and we plug in our I for this particular leg times the 0.5, the half, and we get 44.0 joules of kinetic energy, rotational kinetic energy of the leg. So, conservation of angular momentum means the angular momentum is conserved. The problem with this really is that angular momentum is directional. It is a vector, and so we have to decide on how we're going to determine the direction of that vector. And the way we're going to do it is we're going to use a rule. We're going to establish a rule that everybody in the world will use, and then we can all agree on how we're going to keep track of directions for angular momentum. So here's a skater that's going through this move that we've all seen in skating, where her arms are out and her legs are out. She's going around and around. She has some moment of inertia I and some angular velocity omega, and then as she pulls her arms and legs in, she has a final angular momentum which is equal to her original angular momentum. However, the things that will change is because her moment of inertia I is going to change, and in fact, when she pulls her arms in, it's going to get smaller. And then the omega that she ends up with is going to have to get bigger so that the L can stay the same. And that's why they speed up, because the omega gets bigger, the rotational velocity increases. I'm going to do an example of this here with some numbers. I have a skater spinning at 0.8 revolutions per second with her arm extended. She has a moment of inertia of 2.34 kilograms per meter squared when her arms are extended, and when she pulls her arms in, it's 0.360 kilogram meter squared. Or sorry, 0.363 kilograms per meter squared. So it drops almost by a factor of 10. And we want to know what her final rotational velocity will be, angular velocity, and her rotational kinetic energy before and after she does this move. And so we have the rotational kinetic energy equals 1/2 I omega squared right there. And that's something we'll use eventually. But then initial angular momentum equals final angular momentum, I omega equals I prime omega prime. And we know everything in there except the omega prime. They've given us all those numbers, so we just solve for omega prime. And then the rotational kinetic energy is just 1/2 I omega squared. We got all those numbers. We just plug them in for an initial, for a final, and we find out the final, or the initial kinetic energy that we've got is 29.6 joules, but the final rotational kinetic energy is 191 joules. So how did we add rotational energy to this system? Well, we added rotational energy by using our muscles in our arms to pull our arms in, and the skater did, and then she used her muscles in her legs to pull her leg in closer, and by doing that she actually added energy to her spin. She actually increased the energy. Now the angular momentum was conserved. Angular momentum didn't change, but kinetic energy did change. And that's important to understand the difference, that momentum is not changed by an addition of energy necessarily. And the reason is that the movement of her arms was not changing, was not applying a torque to the system. It didn't increase, it didn't apply a torque, and so it didn't increase the angular momentum or decrease the angular momentum. However, it was capable of adding energy to the system through her muscles, and that the motion of her arms was perpendicular to the motion of her body, the rotational motion of her body, and so didn't add any energy, didn't do any work. And that's the same in like the formation of a solar system. You have this stuff that's rotating around and around with some particular angular velocity and has some angular momentum L. And eventually this stuff starts to gather, it starts to move inward. The motion is around and around this way, but the inward motion of as it starts gathering towards the center and gathering into planets is perpendicular to the motion. And so it doesn't create a torque on the system. It doesn't and it doesn't add any angular momentum to the system. It just adds more energy to the system, or creates, essentially. Anyway, there's energy in the system that is changing, but the angular momentum of the system is not changing. I'm trying to decide if that is actually going to take away energy or add energy. I think that we're actually going to be adding energy into the system to do this. So anyway, trying to decide on that. I have to think about that, but it's not important because we're not going to work on it right now. I suppose we could work it out, because you have the mr squared is the I for each one of these planets, and if they have the same mass as this thing is going to be some fraction times mr squared. And so yeah, the final result actually has more energy than the initial result as those things coalesce, and it's more internal energy. And that energy is bound up in the moment of inertia, essentially. So it has more moment of inertia, and the angular momentum is going to be conserved. In the end, what really happens is that the solar system before it is formed is rotating much faster, and um, as it coalesces into a sun and planets, it actually rotates less fast, and so that energy is internal to the collection of it, but the kinetic energy actually is going to decrease. So it slows down as it forms into a sun. So initial kinetic energy higher, final kinetic energy lower, as those planets form and the sun forms. So a little bit different than the skater. In fact, the opposite of the skater. Okay, so the last part here is we're going to do some collisions with these ideas, where we have linear momentum and then angular momentum. This is the classic one where you have a puck that comes in and hits a stick that's nailed to the table, so that in the beginning there's this linear movement of the puck, in the end there's rotational movement. In this particular collision, we're going to the puck is going to hit the stick and stick to it, and they're going to rotate together. Right? So we start off with some kinetic energy, we start off with some linear momentum, but we're going to calculate it as if it is angular momentum for the ball, for the puck. So right before the puck hits the stick, we're going to calculate its angular momentum as it passes by the radius of the stick. And so that angular momentum is going to be just the I of the stick, which would be just mr squared for the stick, times the omega of the stick. The omega of the stick is actually going to be its velocity at that point. It's linear velocity divided by r, and that's right here. And that ends up just being m times v times r when you simplify it. And that's the initial angular velocity. But then after it hits the stick, you have two i's to consider. You have the I of the ball, or the puck, which is just mr squared, and then the I of the rotating stick, which happens to be 1/3 mr squared. So you have to add those together, and so we do that here. The m times the m over 3, where the big M is the stick. So you have a combined I of both of them, and the initial angular momentum, which is up here, mvr, has to equal the final angular momentum, which is m plus big M over 3 times r squared times, that's my I, and that has to be multiplied by omega of the entire system, which is the thing we're going to solve for, the omega prime. So we end up solving for that here, plugging in all the numbers we have, and we get a final angular velocity for that. Now the kinetic energies, let's take a look at those. We have a kinetic energy of the puck beforehand, and then we have a rotational kinetic energy of the entire system afterwards, and you see that we start with 22.5 joules, and we end with 1.57 joules. So there's a loss of kinetic energy, and that kinetic energy is lost in the sticking of the puck to the stick. Now we talk about the linear momentum of the system. If you have a linear momentum, is m times v of the puck beforehand, and a linear momentum afterwards of the rotating of the stick. Here we can do that, and they do it here. They take essentially an average, which is the linear momentum of the center of the stick, and the mass on the end of the stick, which is the puck. Then you solve for that linear momentum, you get this answer right here, that p prime equals mass plus big mass over 2 times the velocity. And we get that velocity, that tangential velocity of the rotational motion, multiplying the angular velocity times r right here. And we get a final linear velocity of 2.2 kilogram meters per second. And the initial, of course, being 1.5 kilogram meters per second. We actually have an increase in kinetic energy. So you can actually see, we see a decrease in rotational kinetic energy and an increase in linear kinetic energy. So, kind of interesting. Well, this is not kinetic energy, sorry, this is linear momentum. But anyway, what we see here is that linear momentum increases. I think I was saying kinetic energy. I don't remember what I was saying. But anyway, it's linear momentum that increases after the collision, and that's really kind of interesting because we had rotational or angular momentum, which is conserved. We had linear kinetic energy, which we lost some linear kinetic energy, but linear momentum, we actually gained some linear momentum. And that is kind of weird, kind of interesting. Linear momentum, it turns out, is not conserved. Angular momentum is, but linear momentum, when you have rotating things, is not conserved. Angular momentum is conserved all the time. And so that's an interesting outcome that actually has huge implications in physics, that the angular momentum is always conserved, the linear momentum is not always conserved. Here we have an example in sports here where you're holding a racket or a baseball bat or whatever it is that you're holding, and you apply a force to it by hitting it with a ball in some situation. And these things are designed so that if you hit the ball in the right place, you have very little movement because the racket is going to rotate around the point where you're holding it. So where you're holding it moves very little, but the end where you hit it is going to move a lot. And they're designed this way on purpose so that you don't get your hand jarred. If you hit the ball on the throat of the racket or on the or too close to the handle on a bat, then it pushes your hand back. It pushes the whole bat backwards. If you hit it too far on the end of it, your hand gets pushed forward, and so it pushes your hand around. It can really hurt your hand. It can even break the bat or the racket. In fact. So there's kind of this sweet spot where it's supposed to hit right in the middle. So it rotates around your hand. It doesn't jar your hand too much. In this last section, we're going to talk about the direction of the angular momentum. So we have a rotating disc here that's rotating, in this case, counterclockwise as we look down on it. And what we're going to do is we're going to use this rule called the right hand rule, where we curve our fingers in our hand around the direction of rotation, the clockwise direction, with our thumb pointing like we're hitchhiking. And that thumb is going to point in the direction of both the angular velocity and the angular momentum. So that's going to be defined as our direction for our angular momentum vector. So this rotating disc that's rotating on a table or something like this would have an angular momentum vector that points upward out of the table face. If the disc was rotating in the opposite direction, clockwise, then you would have to spin your hand, turn your hand over to get your fingers to curl around in that direction of rotation, and your thumb would be pointing downwards. And so for that clockwise rotation on a table, it's a downward angular momentum. And that direction of the angular momentum is also conserved. So if you have a merry-go-round spinning, for example, in this direction, in this counterclockwise direction from above, it will keep spinning at the same speed of rotation, but it will also stay in that plane. It won't want to rotate into a different plane. It will like to stay oriented, stay pointing the same direction. And so this is used a lot when we're trying to keep ourselves pointing in the same direction all the time. We call it a gyroscope. So, for example, if you have this girl holding this wheel, and we apply this, we get this direction of rotation going around and around and around, so that if we're looking from her left side, this wheel is turning in the counterclockwise direction, which means it has an angular momentum that's pointing out towards her left side here. If she tries to rotate this wheel, if she tries to turn it by pushing down on this handle on the left and pulling up on this handle on her right, then it will respond in a way that tries to get it to go back to where it was. It will resist that rotation. And in fact, it will create a rotation in the system that will conserve the angular momentum. And how does it do that? Well, if we put her on a rotating chair and she turns this wheel like this, the chair will begin to rotate in a particular direction. And let's see what direction that is. Well, here is the original angular momentum, this angular momentum that is pointing, oh, it's actually this one. It's pointing off to her left, this down here. And what it wants to do is, as she tries to change that angular momentum, she tries to create an angular momentum that is pointing downward. That is pointing, because as she rotates this thing downward, her change in angular momentum is going to be downward. And so it's going to try to change it back upward. Well, an upward change in angular momentum would be correlating or correspond to a rotation, a clockwise rotation of a platform that she's standing on in the clockwise direction. And so if she's standing on a rotating platform, that platform would rotate in a counterclockwise direction. And that's an example that we'll do. We'll try to do that in our last lab. We use gyroscopes that are spinning, that have these spinning wheels in them to determine changes in direction just like that. So if you put one of these gyroscopes inside of a car, for example, and you turn a corner, it will show you that you've turned by seeming to rotate, because it will continue pointing in the same direction all the time. It's kind of like a compass. You got to keep it spinning though for it to work. Another thing that we will play around with as we go into our last lab. So that is the last part of chapter 10, rotation of motion, angular momentum, the conservation of angular momentum part. And I will try to get a video up to go through some of the homework for you. But go ahead and get started on the homework, ask your questions so that I can help you with the specific questions that you have. And I'll talk to you later.